I do need to say something. Uh, I do need to apologize to Ava. Yesterday, I overreacted in the lab when we were working on the lab, and something that was not her fault happened. I assumed it was because I didn't explain it good enough or she didn't listen, and it was not her fault. It was my fault completely. There was a hole in the bottom of her gas collecting tube that I gave her that caused everything to drain out. Didn't see it until afterwards. That was my bad, ladies and gentlemen. I'm sorry for that, Ava. I totally overreacted. So everybody else got their lab done. If you weren't here, I put an alternate assignment into your lab for you. The lab is due by the end of the day today, ladies and gentlemen, which means if you do not turn it in by the end of the day today, the best that you can get is a C on it because you lose the opportunity for the extra points for turning it in on time. Okay? So most of you should be done with that. Are there any questions on the lab before we get going today? Yes.
I have like a couple. Do you want me to wait until
Nope.
we have
Do it now. Let's go.
Well, okay, so for number 4, for the calculation for the percent error,
Yep.
we got a negative number.
That's okay.
So what should we put?
You put it as a negative percent.
Oh, okay.
So it's okay if you had 1.2% or minus 1.2%, fine, either way.
Okay. And then for number 2, for the questions.
Yeah.
It says, what was the total pressure of the gas plugs in the tube? Don't give me a number, give me an explanation.
Yep.
Do you want
So I gave you a formula. You calculated it in number 2 above. Explain to me what's in that formula. Okay? If when we did the lab, the only gas we collected was hydrogen gas. Mm-hmm. That's what would be in the tube. That's what would make up the pressure. Okay. But that's not what's in the tube, so just explain that to me.
And then for number 3, what is the value for vapor pressure of water in this experiment based on? What is?
So you found the vapor pressure, right?
Using the chart below.
Yeah. What did you use to find the vapor pressure?
Okay.
Okay. Good.
What was number 4? How was the value for vapor pressure of the water in the experiment found?
How'd you find it?
We used the chart that you gave us.
But that's also number 3.
No. How did you find the actual value?
Oh, by finding the temperature? Or?
Okay, what was the value based on? So you used the chart, but the chart has all kinds of numbers. How did you pick the right one? Okay. That's question 3. Question 4, the chart is actually a what? What is it? What? This would be a what?
Reference?
Yeah. A reference, right? Something where, because it is a known value, it can be looked up online in a reference on a table. Okay?
Did you say that's for number 3 or 4?
That is for number 4. Oh. Number 3, how did you figure out which number to use when you looked at that last page? Okay? Questions? Now, there will be some time at the end of the hour for you to work on things. You can finish your lab up if you are not done. You can turn it in then, or you have it tonight until 11:59 to turn in your lab and get it turned in. Okay? Questions? We are done with the major gas laws for this unit, ladies and gentlemen. Okay? We have done Boyle's, we have done Charles, we have done Gay-Lussac's, we have done Avogadro's. Boyle's, Charles, Gay-Lussac's all roll into combined gas law. I will give you combined gas law on your test. It is one of the 7 formulas that I will give you. I have told you, ladies and gentlemen, that on this page, these formulas at the top, I will give you on the test. They are on the top of the test just like they are here. I will give you standard pressures. 760 millimeters of mercury equals 14.7 psi equals 101.3 kPa, all of that. I will not give you R values. You need to come up with those or have those on your own, or you need to calculate them as you need them. Completely your choice. Okay? Now, ideal gas law also on here. So that is everything that we have covered so far. Today we are going to get into some special relationships, some special things that happen when we deal with gas laws, ladies and gentlemen. Okay? And they are things that we kind of know, but maybe don't completely understand. So here we go, ladies and gentlemen. Let's talk about these things, and let's begin by taking a look at slide 54 in our notes. So again, here's all that information that I'm going to give you. Okay? Here's your standard pressures, ideal gas, combined gas laws, and then these other formulas that we are about to talk about. This one we actually introduced with your lab yesterday. Okay? And that is where we are going to start today. It is called the law of partial pressures. If you have a mixture of gases, ladies and gentlemen, in a container, the gases have to be under what common condition if they are in the same container? Think about the 4 conditions of a gas. What has to be the same about them if the gases are in the same container? Nope.
Volume?
They do have to have the same volume because they are in the same container.
Mhm.
What else has to be the same?
Temperature?
Yes. You cannot have one gas that is hotter than another in a container. Now, the pressure does not need to be the same, and we learned that yesterday. The pressure of the water vapor in your gas collecting tube was far different from the pressure of the hydrogen gas. There was a lot more hydrogen gas in there than there was water vapor, which is why there was a lot more pressure from the hydrogen gas than the water vapor. Now, if you think about it, there are only 4 variables about a gas. We have talked about these. You have pressure, you have temperature, you have volume, and you have amount of gas. If we have a mixture of gases in the same container, they have to have the same temperature and they have to have the same volume. So therefore, ladies and gentlemen, the pressure has to be dependent on what? If these 2 variables are the same. Well, the only other thing that could change for this is what? The amount. It is not a gas law, but it is a relationship that says when you have a mixture of gases in the same container, the pressure that they are going to create is going to be dependent on how much gas there is there. The more gas you have, the more often that is going to hit against the walls of the container. So, law of partial pressure says this: the total pressure of a mixture of gases is equal to the partial pressure of each gas in the mixture. All gases have to be at the same temp, and all gases are occupying the same amount of volume. The moles can be different and the pressure can be different. The formula is simple, ladies and gentlemen. The total pressure is equal to the partial pressure of however many gases you have in your container. Yesterday, how many gases did we have in our container? 2. What were they?
Water vapor?
And?
The hydrochloric gas?
Nope, the hydrogen gas that was created in the experiment.
Yeah.
The hydrogen gas. So, ladies and gentlemen, that formula stopped after there because there were only 2 gases. If you have 3 gases, it goes there. If you have 4, you need another one. This is just dependent on how many gases there are in the container. And all it says is that if each gas has a certain amount of pressure, you add them up and that gives you the total pressure. That is all we are doing here. Okay? So gases have a total pressure of 15.6 psi. Gas A has a pressure of 3.58 psi. Gas B has a pressure of 4.9 psi. What is the partial pressure of gas C? Plug things into our formula, ladies and gentlemen. Now this is the simplest one. Why? This is an addition problem. What plus what plus what equals 15.6? There you go. That's your problem. So we are going to take these 2 numbers and you can either add them together right away and then subtract them from both sides, or you can subtract these 2 numbers from the other side as well. Why? To get pressure of C alone. Questions? Again, this is one of the easier gas laws there is, and I will give you the formula. All it says is if you have gases mixed together, their pressure should add up to the total pressure. Questions? Okay. So now, because the pressure is dependent on how much gas is in there, we can have this relationship, ladies and gentlemen. The total moles in a mixture of gas is equal to the moles of each gas in the mixture. So again, all of the gases have to be at the same temp. All of them have to be occupying the same volume. The moles of the gas can be different and the pressures can be different. The moles can be different and the pressure can be different. But whichever gas you have more of, more moles, is going to create more pressure. And the formula, ladies and gentlemen, is identical to the last one, except mole total is equal to the mole fraction, they call this instead of partial pressure, of each of the different gases involved. So if you know the total moles in there, ladies and gentlemen, you could figure out how many moles were from one gas, how many moles were from another gas. Okay? So again, a mixture of gases contain 4.35 moles. If there is 1.12 moles of gas A and 1.25 moles of gas B, what is the mole fraction of gas C? Put everything into your formula, ladies and gentlemen. Calculate it. Questions? Okay. But what it is also going to mean, ladies and gentlemen, is what our next gas law is, which gets a little bit more, not intense, but just takes these two relationships and puts them together. Okay? If a mixture of hydrogen gas and oxygen gas has a total pressure of 545 millimeters, and there are 2.35 moles of hydrogen gas, how many moles of oxygen gas are in the mixture? Okay? So, we've got a total pressure, we've got a pressure of hydrogen gas, we've got a moles of hydrogen gas. Okay? We want to know how many moles of oxygen gas are in the mixture. So what we are going to do, ladies and gentlemen, is set these two things equal to each other. Because the number of moles affects the pressure, we can set these two equal to each other in a proportion. The moles of A over the mole total is equal to the pressure of A over the pressure total. So in other words, if half of your moles come from one gas, half of your pressure is going to come from that gas, whatever the pressure is. Now up here, I've got two gases, hydrogen and oxygen. It doesn't matter which one you call A and B, okay? A just means one of the two. So we're going to take the numbers from above, ladies and gentlemen, and we're going to put it into this formula. Now I have the partial pressure of hydrogen gas, and I have the total pressure. That goes here. I have the moles of hydrogen gas, but I don't have the mole total. Now you may be sitting there going, well, Mr. Brand, didn't they want what? What did they actually want us to find here? So why am I finding the mole total if they want us to find the moles of oxygen? So that eventually we can find the oxygen. If I know the total and I know how much of the moles of the hydrogen gas, I can solve it. Okay? I can solve it. So again, from here, ladies and gentlemen, cross products are equal. Put it all on one line. Get moles alone eventually, ladies and gentlemen. Okay? Get moles alone. So then when I get moles alone, ladies and gentlemen, I have 2.35 moles times 785 milliliters over 554 milliliters. Milliliters and milliliters cancel. I will get the total moles in the container. How do I then get the moles of oxygen? Take the total minus the moles of hydrogen. You will be left with the moles of oxygen, ladies and gentlemen. Questions? Now, this is a proportion, correct? This here? There is another way of doing this problem. There are multiple ways of doing this problem, ladies and gentlemen. Multiple ways, okay? I'm going to show you another one that you can use if you wish, but it's not the way I presented it to you. In this problem, ladies and gentlemen, ultimately I have certain pieces of information that I can and cannot use, okay? So, information that I have that I can use, ladies and gentlemen, is as follows. I have got the P total, 785 mmHg. I have got the pressure of the hydrogen gas. That is 545 mmHg. I didn't calculate it, but what else could I find here? Do I have the pressure of the oxygen gas? Yes or no?
Well, you can find it.
How would we find it?
The 785 minus 545.
If we subtract these two, I will get the pressure of the oxygen gas, ladies and gentlemen. Pressure of the oxygen gas is 240 mmHg. Okay, I can get that pressure. Okay, now I've also got the mole total. I do not have the mole total. Sorry, ladies and gentlemen, hang on. I have the moles of hydrogen gas. That is 2.35 moles. I do not have the moles of oxygen gas, and I do not have the mole total. Okay, I don't have either one of these. That's why I couldn't directly go and figure out based on the partial pressure of oxygen and the pressure total. But, ladies and gentlemen, what I could do if I wanted to is I could do this. In this ratio, ladies and gentlemen, I can set up this ratio in any way. What I mean by that is I have got the pressure of the oxygen gas and I have got the pressure of the hydrogen gas. I can set that equal to the moles of oxygen gas over the moles of hydrogen gas. I could do it this way as well. The main thing is, ladies and gentlemen, if this is a partial pressure, this is a mole fraction and therefore the same gas. If this is a partial pressure, this is the mole fraction and therefore the same gas. This formula works, so will this one. Okay? So will this one. And for this one, ladies and gentlemen, I've got three things that I can put in right away for it so I can get the moles of oxygen directly. Your choice how you want to do it. I can put in the pressure of oxygen, 240 mmHg, over the pressure of the hydrogen, 545 mmHg. That's going to be equal to the moles of oxygen over the moles of hydrogen. The moles of hydrogen is 2.35 moles. I can now solve this, ladies and gentlemen. I can now solve this, okay? And again, it becomes the same solving as this one here is. I'm just solving for the moles of oxygen directly. Moles of oxygen times 545 mmHg equals 240 mmHg times 2.35 moles. This number I'm going to divide by 545 on both sides. What I do to one side, I'm going to do to the other. And I'm going to be left with the moles of oxygen, which is 1.03 moles. Either way, you're going to get the same answer, ladies and gentlemen. Questions? This formula here, ladies and gentlemen, is a proportion. You can sub other things into it. So you can do the, whoops, sorry. So as well as the moles of A over the mole total, you could do the moles of A over the moles of B is equal to the partial pressure of A over the partial pressure of B. I don't care what you put on the top and the bottom. It's up to you. They don't have to be totals on the bottom. They can be partial pressures as well. Either one is okay to use. Questions? Okay. Austin, Farhan, if you guys want to take a nap, Miss Ferk will let you do it down in her office. Go ahead. Come on. Okay. Two gases are under the same set of conditions at the same volume, temperature, pressure, and number of moles. They have the same kinetic energy. Therefore, the square root of their masses is inversely proportional to their velocities. So here's what we have, ladies and gentlemen. We have two gases that are in the same container, the oxygen and the nitrogen in the air here. Okay? Which gas is moving faster, ladies and gentlemen? Which gas in the air that we are breathing right now is moving faster, and why? What?
Aren't they moving the same?
Okay. They're at the same what?
Temperature?
Which makes them the same what? What is temperature actually?
Kinetic energy?
Kinetic energy. Yuritsi and I run a race. We finish with the exact same kinetic energy. Who wins?
Her.
Why?
Less mass.
So she has to move faster. We cannot have the same kinetic energy if we are moving at the same speed. She has much less mass than I do. Watch. Okay? So if her and I are moving at the same speed, I will have more kinetic energy than she does. If we were gases, that would mean I would be at a higher what than she is? If I have more kinetic energy than her, what does that mean? Nope.
Pressure.
No.
Amount.
No. Temperature. Thank you. Temperature.
Really?
Kinetic energy is temperature, correct?
I guess
So if I have more kinetic energy than she does, what would that mean for my temperature? Would be higher. The question says, we finish the race with the same kinetic energy. In other words, we are at the same temperature. What is the only way that she can be at the same temperature of me if she has less mass than me? She has to be moving faster. So think about it, ladies and gentlemen. This room is made up of nitrogen gas and oxygen gas. What's the temperature of both gases? The same, which means their kinetic energy is the same. Which gas is moving faster? Why nitrogen? Nitrogen is a lighter gas than oxygen. How do you know? Formula mass off of the periodic table. N2, 28.02. Oxygen, 32. Why? O2 again, remember? Oxygen has more mass. Nitrogen has less mass. The nitrogen has to be moving faster, ladies and gentlemen. So under the same set of conditions, a lighter gas will always be moving faster than a heavier gas. Under the same set of conditions. Here's what it comes down to. The kinetic energy of both gases is the same. Why? Because their temperature is the same. What does kinetic energy depend on? Well, kinetic energy is 1/2 mv squared. So the kinetic energy of gas A is equal to 1/2 its mass times its velocity squared. The kinetic energy of gas B is 1/2 its mass times its velocity squared. Okay? This is the formula for kinetic energy. Now, what can I do to this formula right away to these 1/2s? I'm going to get rid of them. They're the same on both sides. So I'm going to get rid of them. I'm going to drop them. Get rid of them. So now mass of gas A times velocity squared of gas A equals the mass of gas B times the velocity squared of gas B. I now want to get it so that the conditions are the same on both sides of the equations. In other words, I want the masses on one side, I want the velocities on the other. So I'm going to take and I'm going to divide this side by the mass of A, put it on the bottom here. I'm going to take this side and divide it by the velocity of B, put it on the bottom here. That is how we get this. What do you notice about A and B on each side here? They're reversed. This is not the same as the last gas law where they were the same on the top and the bottom. Okay? This is now reversed. Now, next thing, ladies and gentlemen, I don't want to leave a square in here. Okay? By the way, what can I use for masses here? What did we just talk about? Oxygen and nitrogen. What did we use for their masses?
Their formula mass?
Yeah. Formula mass can go in here, ladies and gentlemen. Formula mass can go in here. Okay? So, the problem is to get this so that these are not squared, I have to take the square root of this side. What I do to one side, I have to take the square root of another. So this is what your formula looks like, ladies and gentlemen. So if you know how fast one gas is moving, you could find how fast the other gas is moving because we can definitely find their masses simply by knowing what gases they are. But the lighter one is always going to be moving faster. Okay? So, find the velocity of hydrogen sulfide gas that is under the same conditions as carbon tetrachloride gas, which has a velocity of 1.45 meters per second. Now, people will look at this and go, Mr. Brand, you can't solve this. There's only one number there. That's all you need for this problem. That's all you need. Because we're going to assume the amount of gas is 1 mole. They're under the same set of conditions. They're at the same pressure. They're at the same temperature. They're at the same volume. Guess what? That means there's the same amount of gas there. So let's assume 1 mole. Okay? When we do that, ladies and gentlemen, this is the formula that we are going to use. For gas A, hydrogen sulfide. Hydrogen is 1.01. Sulfur is 32.04. That gives us 34.08. Carbon tetrachloride is CCl4. 1 carbon, 12.01. 4 chlorines, 35.43. Gives us a much heavier gas. Which gas is moving faster? Which one? Yeah. A lot faster? Quite a bit, yes. Because it's a lot lighter. Right? When we plug this into the formula here, we have the numbers we need for this side. We have the mass of these two gases. We also have a velocity. Now, because you get to pick gas A and gas B, ladies and gentlemen, I always leave the one that I am solving for on the top. I don't want to solve for the one on the bottom. You can, you still could. I just always solve for it being in the top position. So I decided that this was going to be gas B, the carbon tetrachloride, which means if it's on the bottom here, it's on the top here. Here's the other gas. Here's its velocity. Now we are simply going to solve this. Yes, you're going to put numbers into your calculator. Yes, you're going to use the square root button. But all you have to do is take this side and multiply it by 1.45 meters per second. And you get the velocity of gas A. 3.08 meters per second. Questions? Last thing we'll talk about for today, gas densities. We mentioned this before. Density is an intensive physical property. Intensive property means that it does not depend on sample size. Doesn't depend on sample size is a great thing for us because we can pick any sample size that we want. Any one that we want. Okay? Intensive. Choose a sample size. Okay? What is the best sample size to choose that we are finding in this unit? Why? Because first of all, it relates to volume at STP, correct? What's the volume of 1 mole at STP? And it also relates to, which is important for density, mass. We did volume, yes. But it also relates to mass. So by picking 1 mole, ladies and gentlemen, you get the mass of a gas and you get its volume if it's at STP. If it's not, we can find the volume of the gas if their pressure and temperature are different. Use combined gas laws. Use ideal gas law. I don't care. Either one. Okay? So the only thing about a gas that can change to affect its density is volume. You cannot change its mass. So therefore, ladies and gentlemen, if we're at non-standard conditions, we find the volume at those non-standard conditions. You can use PV equals nRT. By the way, what is missing from here to use PV equals nRT? Please don't say R. We know those. What is the density of oxygen gas at 11.5 psi and 45.0 degrees Celsius? What? Yeah, but that's what we're going to solve for. What else is missing? What did we just say? 1 mole. Okay? 1 mole. Okay? Oops. So, we can use combined gas laws to compare to STP. Our temperature 45, add the 273, 318. Formula mass of O2, 32.0 grams per mole. Here we go. Solve for the volume. Volume, ladies and gentlemen, is 33.4 liters. Using combined gas laws. We could, ladies and gentlemen, use ideal gas. If you want to use ideal gas, ladies and gentlemen, here's what it would look like. PV equals nRT. Same pressure we would have from up here. We would use 11.5 psi. We are solving for volume, ladies and gentlemen, so that we can use it for density. N equals 1.00 mole. R for psi, what is it? What's the R value for psi?
R value, the ones that equal each other?
Yep. 1.21 psi times liters, mole times Kelvin. What's our temperature here? Which is 318 Kelvin. So divide this side by 11.5 psi. What I do to one side, I do to the other. Volume still equals 33.4 liters. Either way you do it, ladies and gentlemen. Either way you do it, the volume is going to equal the same thing. Questions?
Where'd you get that 1.21 for PSI?
That's the R value for PSI.
wouldn't it be, cause I asked and you said it's the ones that equal each other, wouldn't it be 14.7?
Those are equal pressures. The R values are also equal to each other. The 62.4, the 8.31, the 1.21, and the 0.0821. Those are also equal to each other. So you're right. The pressures are
Ideal gas law.
the pressures are equal to each other, and so are the R values. Questions? So again, ladies and gentlemen, I've said it before and I will say it again. Two people do the same problem with two different formulas. They will get to the same answer. By the way, what haven't we done yet? We haven't done density. All this was just to find volume, ladies and gentlemen. Density is equal to mass divided by volume. Density equals 32.0 grams divided by 33.4 liters. Now you find your density, ladies and gentlemen. Probably about 1.03 or somewhere in there. Something like that.
Would we always compare it to STP?
Here's the thing. You can always compare it to STP. So when it doesn't give you a second set of conditions, use STP for those second set of conditions. Okay? Yes. Yes, I do. Thank you. Because here's the thing. These three numbers here, somebody take and put them into their calculator and do this math. Take 14.7 times 22.4 divided by 273. Tell me what you get.
It's the R value.
Yeah, that is the R value. So whether you use an R value or you compare two standard conditions, they're the same, because the only thing that's missing in here for your R value is what?
1 mole.
1 mole. Since it's 1, it doesn't change it.
So when we're doing this, we can just make it equal to the R value.
Yeah. That's why it's the same. That's why it's the same. All right? It's equal to the R value. Questions? All right, ladies and gentlemen, you got about a half an hour left to class. The worksheet that I gave you, Packet 2, has plenty of problems that you can do now. The only one I haven't shown you, ladies and gentlemen, is the last formula about the densities being proportional to the masses. But every other one on there I have given you. Okay, we'll finish that one up tomorrow, ladies and gentlemen. So, get some practice time in. Get some work done on this, ladies and gentlemen. Okay? If you have questions, let me know. And, by the way, make sure, get your lab done and turned in today, ladies and gentlemen. Go to work. Go to work. Go to work. Go to work.
Can I use the bathroom?
I was about to say that too.
What?
Computer from the library.
You need to wait until they get back.
Yes.
Okay.
What is dense? Never mind. I got it.
What is what?
I got it.
Okay. What? Yep, that was what I was talking about. Olivia? Jennifer?
Exactly.
You got half an hour. You got time to practice things. In a day, we're going to give you some of the tests. This one, I don't know how to do these. Here's your chance to practice and here's your chance to get some help while I'm here in the room.
No, not that. Wait. Oh, yeah.
Do I get this?
So then that is.
Wait, are you doing it?
2 point.
Or is it-